Hi everyone, my name is Chris. I'm an OpenSciEd teacher and facilitator in Connecticut, and I'm here to share with you lesson 16 of the weather unit, which focuses on the question how to warm air masses and cold air masses interact along the boundaries between them. It's a really intriguing lesson, especially if you enjoy math and graph analysis, which are both heavily featured on day 2. Enjoy them. Let's chat for a moment about how we got here. During lesson 15, we figured out that there are these big sort of chunks of air that are called air masses that can get defined by having similar temperature and humidity levels. And that these air masses, when they meet each other along fronts, seem to be where storms and precipitation occur. So we're left wondering, well, when these two things do meet, when warm air masses and cold air masses interact, what happens? And that's what we're going to investigate next. Let's see the structure of the lesson here real quick. It is an investigation lesson using data analysis. And it is a 2-day lesson where I left 60 minutes in place for material prep because the lesson has a demonstration on day 1 that takes a little bit of practice. I'll say a little bit more on the tips and tricks side of that. There is not a hands-on investigation. There is a good demonstration. No devices are required. However, it is suggested that you video the demonstration, and that is best done from the side, and I'll explain that in just a moment. The lesson is 2 days long. Each day is divided into 2 not quite equal chunks. Let's dig into each day. Day 1 has 2 large chunks. The first centers on a demonstration using cold and warm water to represent air masses. And then the second is a larger, longer sense-making discussion that helps to make sense of what you see during the demonstration. The key moments on day 1 come when you're trying to map the components of the demonstration to the real atmosphere, and when you're having that longer discussion about how to make sense of what you just saw. On day 2, I've divided this one into 2 parts as well. Initially, there's a short revisit of the demonstration and modeling what happens when 2 air masses meet. Then there's the second half, where students use graphs and data to explain why water vapor condenses into droplets and forms clouds. I have to be honest, I'm thrilled if my kids understand the conceptual part of this day, part 1, and I hope that the math resonates with some of my kids, especially my computational thinkers. They really seem to enjoy it, but it is a bit of a challenge. So let us move ahead and see what we figure out. So this lesson is a little hard for students, and it's worth keeping you and their focus on the lesson question, which is essentially what happens when 2 different air masses meet, and maybe how might that help us predict the weather. I simplified what we figure out a little bit. But because the key to it is that warm air masses meet cold air masses, and the cold air pushes the warm air upward due to density differences. That the most amount of water vapor that can be in air is called 100% relative humidity, and that warmer air can hold more water vapor than colder air, so it can have a higher relative humidity. If you cool air that is already at 100% humidity, it will cause condensation to occur. Those are the key figurings out from lesson 16. Let's check out those key moments. Here we go. The first one that I chose is part 2, where they map the components of the demonstration. And don't skip or underestimate the importance of this. If you really want kids to understand why you're using aquariums and water to talk about air masses, you can't skip this part. And ask it a bunch of times during the demonstration too. What is the warm water in our atmosphere? What is the cold water in our atmosphere? And make as many kids as you can say the words and refer to their mapping of the demonstration. There is a sample for this in the teacher's guide. It's already filled in for your reference. And student voice in the how is this similar or different to the atmosphere was a little bit challenging. Um, and so go with whatever you can get to. It doesn't have to be perfect. Uh, then you do the demonstration which leads you to this building understandings discussion. And the conversation seems so really simple, and it can be simple if you focus on the two key takeaways. The first, that warm water moved upward and stayed on top of the colder water, and the cold water moved underneath and stayed on the bottom. At this point, there's a temptation to connect this back to the atmosphere already, but you don't need to do that today. That's how tomorrow starts. Stick with what they saw and uh, labeling the reason for what they're seeing as density, which is a topic they're already familiar with. As you begin day two, this is potentially a bit of a frustrating sequence. There's a set of images that show a idealized version of what a warm front looks like when it runs into a cold front, and what a cold front looks like when it runs into a warm front. And they make some models on their own first, and then all of a sudden you unveil these images for them, and they're like, "Why didn't you just show us this before?" But this is where you have to actually celebrate with them, because they will have gotten a bunch of the parts absolutely correct. But they might not have thought of others because they weren't in our demonstration. For example, we didn't see clouds form in our aquarium demonstration. So use those as sort of celebrations of things that they did know and understand, and then to motivate into this um, water vapor, relative humidity, percent graph madness that's coming up next. Because they're going to need a little motivation to stick with that. And then we come to the last part where we revisit our weather model. And this is like the great moment. It's like one of those deep breaths moments. You will have just spent 20 or more minutes walking your kids through math and graphing and relative humidity and how it changes based on temperature and why water vapor is condensing. It's a lot. But this is a great time to say, let's leave the numbers behind for a few minutes and see if we have the general ideas, which are that air masses move and collide along fronts. Warmer air always moves upward and begins to cool. As air cools, it can't hold as much water vapor. The water vapor condenses into drops, or perhaps forms ice and forms our clouds. Um, I actually also found here that a visual can help. If you taught the thermal energy lesson, there's uh, in lesson 4, they do a lid, no lid explanation about why a lid helps a cup stay, and they use little particles to represent physical things to represent the particles. And that can really help here. You can actually have the warm, humid air leaving the ground, going up, cooling off, and then some particles have to leave, but where do they go? They go into clouds. So some visuals here could potentially help. Let's talk about a few tips and tricks for you here, especially around that demonstration. The demonstration is kind of the hardest part, and really the hardest part of all of it is the barrier that has to go in the middle of the 10-gallon aquarium. My aquarium had a little lip on the inside that I had to kind of cut off to make it able for it to slip up and down easily. I also had to think that it might be worth considering making the barrier out of something a little bit stronger, like some thicker pink foam insulation. But either way, when you are adding the water in the demonstration, make sure you have someone hold the barrier, because they're made out of foam and it can float out of the way. You don't really need to worry about removing the barrier quickly. Being slower actually can be a little bit helpful for students because it helps them sort of see everything better. I also found it really useful to pre-make cold blue water gallon jugs, because you use about a gallon of water on each side of this barrier that you see here. The blue on the right is cold water, the clear on the left is warm water. So having it pre-made blue cold water really helped out a lot. And the more the difference of temperature between these two sides, the greater the better the effect will be in the aquarium itself. So you can find a way to keep your water super cold or make this water on the left super warm. That really does kind of help out a lot. And if all else fails, there is a video that you can watch of this, and you don't have to actually do it yourself. There are a few words that get used along the way here. Air masses, certainly frontal boundaries or fronts come into play a lot. Relative humidity and percent and saturation all are a part of this lesson. Humidity and temperature are carried over from previous days. And there are really only three charts or interactions that come out of this. One is the warm and cold water interactions chart. The second is using the graphs of relative humidity data. And then lastly, the modeling of interactions at a front, which gets sort of co-created as part of that consensus discussion. So I hope this has been helpful. If you want to see what's coming up next, please go ahead and check out the Lesson 17 video.